All right. Hope you can see my screen.
Yes, sir.
All right. So let me brief you on Lagrange-Euler dynamics before we get going again. The first thing you need to do if you want to develop the Lagrange-Euler dynamics is start from this equation here, dq, the inertia matrix. So if you look at the expression here, you can see you need to know the masses of the links of the manipulator, and also you need to know the Jacobian, okay, of the manipulator. And also you need to know, I mean, when it comes to Jacobian, there are two forms. One is the linear velocity Jacobian, the other one is angular velocity Jacobian. So when you write down your forward kinematics equation, right, you have to write down not only for x, y, z position, but also the orientation angles. That also you have to write. And then you get velocity Jacobian as well as linear velocity Jacobian as well as angular velocity Jacobian. Okay. And you need to know the inertias, right? Of the links with respect to the base coordinate frame. Okay. So once you do all these things, you can multiply. It's a lot of labor, and eventually you get to this 2x2 matrix. Okay. And we identify the items in the matrix as D11, D21, D12, and D22, as you can see it over here. And we have proven earlier that this matrix is a symmetric matrix, okay, and therefore off-diagonal elements are equal. This is a 2x2 case because it's a two-link manipulator example. So you have four D elements here, right? And the dimension is two-link, two-joint manipulator. So you have this first item or term in the Lagrange-Euler dynamic equation as equation 1.51. Next thing is you take the D elements here, D11, D21, D12, and D22, right? And then you use these equations over here to determine the Christoffel symbols of first kind, right? For a two-link manipulator, you have 8 Christoffel symbols, 2 to the power 3. And standard equation for Christoffel symbols, you have it and use it to calculate these things. You don't have to derive anything, it's already there. Just use it. Once you have the 8 Christoffel symbols, you regroup them into 2 subgroups. One is the Coriolis forces and torques, the other one is centripetal forces and torques, right? So there you can see this separate arrangement into 2 subgroups. Then you can see the first term over here is dot squares, okay? So they are coming from centripetal forces and torques. And the second one is Q dot times Q dot, right? The coupling between different links here. So that is the Coriolis term here. So that is the second term of the Lagrange-Euler. And third, what you do is you calculate the distance from the base to each and every link, right? These RC1, RC2 are these position vectors of the joints, the links rather, and then use the potential energy expressions to calculate the third term in the Lagrange-Euler dynamics. I think we have done all these things. I'm just giving you a little summary, right? So you know the steps involved. And the equation 1.59 is the potential energy term, right, in the Lagrange-Euler equation. So when you regroup it to the formal G of Q, you get this one. All right. Now, what you want to do next is to combine all these inertia terms, Coriolis and centripetal term in the middle, and the gravity term next. Combine them together, and that is your torque over here. So in that way, it is pretty very well structured approach. Okay. So if it is a 3-link, 4-link, 5-link, what will happen? This becomes bigger in scale. There's a lot of combinations, but process will be the same. So if you want to do it manually, it's very, very difficult, time consuming, very tedious, but now you have symbolic mathematics, right, on MATLAB and all that. So you can use one of these platforms and work with symbols so that the computational platform will work it out for you. Okay. Now, today we are going to break down this Lagrange-Euler equation we derived for a 2-link manipulator, right? Tau 1 and tau 2. And I'm going to expand it for tau 1 first. And this is the tau 1 expression. All right? Tau 1 expression. The first joint torque is coming from this equation, Lagrange-Euler. You can see the first term over here, this times Q1 dot, double dot, and this term times Q2 double dot, and this term is 0. This term times Q dot square, Q2 dot square rather, and then minus M2 L2 L1 sine Q2 times Q1 dot Q2 dot, and the first term over here, right, is the gravity term, is equal to tau 1. Okay, so let's focus on this, because even though it is mathematically tractable, what is it physically? We need to understand what's going on here, even though we have the equation. Now let's take the first term. So altogether, how many terms are there? The first one, second, third, fourth, fifth, and sixth. Sorry, fifth. Altogether, 5 terms are there. So we need to figure out, the purpose here is to understand each and every term here, so that you know what these mathematics actually tell about the physical phenomena, right? So this tau 1 is the first term over here, right? So then I describe the entire term here. So if you look at the manipulator like this, the first link and the second link, right? Let's assume this is just one object like that, right? So this joint you can forget for the moment, because when I raise my hand from the shoulder, right, when with this joint locked, I have to move the entire thing, right? First link, second link, etc. The whole thing should be moved by joint 1. So therefore, if you look at the 2 links as just one link together, right? How much of a torque is required at joint 1 to actually just keep it there and then move with some acceleration. Okay, so that torque is tau 1, and you can easily see it over here, m1 L1 square over 3. So this is the inertia of the first link, right? Inertia of the first link as seen at this point, joint 1. Okay, joint 1 is a point where you generate the torque. So if you look at the first link, right, not the inertia at the center of gravity, but when you transfer it using the parallel axis theorem to the joint, right, it is m1 L1 square over 3. So this first term times theta 1 double dot. So of course you understand this one. Inertia times angular acceleration is the torque. Okay. What about the other terms? Right. if we look at this term over here, right? Entire thing, look at that one. The second link, right? Second link, you can see that over here, is actually this far away from J1 point, right? L1 square plus L2 square over 4 plus 2L1 L2 by 2 cos Q2. This is cosine theorem applied on this triangle, right? This is L1, the base length. The other side is L2 over 2. And what is this distance? Of course, this is the equation. And there is this mass here, m2 L2 square over 12, right? So that is the inertia at the center, right, of gravity. And what you want to do is, you have this inertia at the center times, and then you apply the parallel axis theorem, right, to calculate the inertia over here. Then you need to get the square of this one, right, the length. So, and then to transfer the inertia to joint 1 position. All right. So you get the inertia here, m2 L2 square over 12, and then add onto it whatever coming from the parallel axis transfer. So that is this part over here. Okay. So, and it is also moving at Q1 double dot. Because when you actuate this joint, link 1 and link 2, they're both having the same acceleration. Even if you, let's say you lock this joint over here, right, elbow joint, and you move from the shoulder, this link and this link both are moving at the same acceleration. We are still not talking about the motion of the second link, right? This one, we are not talking about that yet. It's about the first joint. So we understand, yeah. So this is the mathematics, and now we understand it physically, right? The first joint inertia, first joint is connected to the joint itself. The second link, or the first link, the second link is not connected to that joint. So therefore, we have to get the inertia at the center of gravity and then transfer it using parallel axis theorem. So we get these two terms. Okay. So tau 11 is completely understood. We have no doubt whatsoever about what is this term here, lengthy term here, right? And there's no point of remembering it if you do not understand what it is, right? Now we know this is the inertia of the link itself, but you cannot simply multiply it with the angular acceleration because this link is not directly connected to the joint you are referring to, joint 1. It's far away. Then you need to do the parallel axis transfer of that inertia as it is seen by the joint 1. Okay. What is the second term? T12. That is this one. This comes m2 L2 square over 3 plus L1 L2 over 3 cos Q2 times Q2 double dot. So what is that? Tau 12. So if you go on reading this little term here, link 2 accelerates with Q2 double dot. So link 2 has some angular acceleration like that, right? And torque generated by joint 2 for this is m2 L2 square over 3. So for that, joint 2 generates this torque. But joint 2 is not fixed to the earth. It is connected to the end of the link 1. It's in the air. So when it produces a torque, it produces it while sitting on at the end of link 1. Okay, it produces the equal and opposite torque on the link that it is sitting on. So therefore, link 1 feels this torque. All right. So this torque couples with link 1 as shown in figure 1.8 left. So you can see it over here. you got this link 2 here, and it accelerates. You can see Q2 double dot, and this is the inertia, M2 L2 square over 3, right, as in from here at the joint, right? So it generates that torque over here, all right? The Q2 double dot is the acceleration of link 2, and the torque required for that is this much. So it is applied on link 1 at the end of link 1, right, in the opposite direction. So when it comes to a torque, it doesn't matter where it applies. It's the same torque wherever it is, right? So therefore, with the second link having some sort of acceleration, because it produces that torque at the end of link 1, the link 1 will deflect downward, right? If it is like this, when you start moving, the link 1 goes down. That is unacceptable. That's a disturbance. It's not what we expect. We expect link 1 to be at that point, configuration, and link 2 moves without any motion in the link 1. So in order to do that, what link 1 does is, in fact, joint 1 does is, it produces this additional torque as well. So therefore, not only tau 1, right? Not only this much torque, now it has to produce the second term as well. Okay. Now, you can see it over here. The torque couple, this torque couples with link 1 as shown in figure 1.8 left, what I showed you just a while ago, and cause an opposing disturbance. So joint 1 requires to generate the equal and opposite torque, right? That is tau 1 to 1. That is this one, tau 1 to 1. Can you see it over here? Tau 1 to 1. The same torque, but in opposite direction to the to this particular torque that is happening at the end of the link 1. Now, when you get the opposite of that, then it will be as same direction as the torque of the joint 2. So joint 2 has a torque in certain direction, and joint 1 has to generate the same torque at joint 1. Okay, right. So not only that, because this is angular acceleration, right? So when you have this angular acceleration of the second link, you can see it over here, second link. You look at the center, right? If you assume the entire mass is concentrated there, right? This point has a linear acceleration as well. So for every angular acceleration like that, all the points here are going to assume a linear acceleration as well, right? That is the distance times angular acceleration. So if you look at the center, the distance from the joint is L2 by 2, and the angular acceleration is Q2 double dot. So the acceleration at the center is the product of these two, right? L2 by 2 times Q2 double dot. Can see over here, right? So the mass is M2, so it requires this force. So there's this force at the center of link 2. All right. Now this force is also felt by link 1 at the end. How do we calculate the force felt by link 1 because of the acceleration of link 2? It is by resolving this force into two components, right? One is, as you can see it over here, so this is the reflection force over here, F, the same force but in opposite direction. And you separate it into two, resolve it into two components, horizontal and vertical in this configuration, but horizontal means actually along link 1. Vertical means normal to link 1. Okay. So here I have drawn link 1 as horizontal. That's why you sometimes could get this misunderstood. The force should be resolved into two components. One is along the link 1. The other one is normal to link 1. So the normal force to link 1 is F cos Q by 2. Sorry, F cos Q2. Now you have the situation at the end of link 1. At the end of link 1, there's a force downwards, right? So now you calculate the torque on joint 1 because of that. Right? The torque is distance times force, and distance is L1 this time. L1 times F cos Q2. So that is L1 times M2 L2 by 2 cos Q2 times Q2 double dot, right? So that is this term over here. All right. Can you see that? The first term is because of the acceleration of the link 2. Second one is because of the first one is angular acceleration of link 2. Second one is the linear acceleration of the link 2 at the center of gravity. All right. What else? So that is tau 1, 2. Let's walk through the rest. And next thing is tau 1, 3. That is this component. So what is that? Let's find it out. Tau 1, 3. Further down, tau 1, 3. So for that, look at these two diagrams. This is the torque joint 1 requires to compensate the reflected torque due to the centripetal force, Fsen. You can see it over here, Fsen, centripetal force of link 2. So that is now when an object is in circular motion, right, it tends to move outward because there's a radially outward force, right? And that can deflect the entire manipulator if you do not have a opposing force for that, okay? So this is the Fsen, centripetal force due to the rotation of Q2, okay? Rotation of L2, rather, the second link, okay? And as you know, from circular motion theory, this force is proportional to the angular velocity square of the rotating body. That is Q2 dot square, Q2 dot square. Okay, so you can see it over here, tau 1, 3, that is this one, right? Q2 dot square term. So this is coming from because of this centripetal force. Now, if you break it down and you look at the vector direction, right, it is like this, centripetal force. And if you break this down into two components, you can see one is along the link 1, other one is normal to link 1. So along link 1, we do not consider here because any of these forces along the link, either outward or inward, is actually taken up by the structure itself, right? So it's like you have this link here, and there's a force from this side, or like pushing downward or pulling upwards. Either way, the motor at joint level does not have to do anything with that force, okay? It's actually acting along the link. But the normal force is what the motor has to be concerned about, right? This normal force is this force times sine q2, and it is happening at this length L1. So L1 times sine times the force. Okay. So that is why you see the term over here, L1 times sine Q2 times the rest. Okay, fine. What is the next term? This one. So that is the fourth term, tau 1, 4. Let's work it out. Tau 1, 4. It's over here, right? Is the torque joint 1 requires to nullify the reflected Coriolis force from the link 2, as shown in figure 1.9, right? So this is the illustration for you to understand what is this Coriolis force, right? Coriolis force. So Coriolis force is a force acting on an object which is actually moving with a linear velocity while it is rotating, right? Having some angular speed. So it looks like, let's say you have a cannon, and you rotate it, and you keep firing, right? You keep firing. You rotate and keep firing. So if you are the gunner, you will rotate with the cannon, right? You will rotate with the cannon, and you see it's going straight. But you see when you look at the rotation also, you come out of that frame and you will see it is turning rightward, right? Like that. So that is the Coriolis force. So you can see a lot of YouTube videos on Coriolis force to figure that out, the physical phenomena. And also it's very close to some people living in Florida or Hong Kong, in that area where you get a lot of cyclones, right? When the cyclone takes place, gets in shape like circling moisture, you can see the eye of the cyclone, and it start moving upward, and you will see gradually it is now turning rightward, right? Sometimes this turn helps the cyclone not to uh, uh, enter the coastal areas of some of these countries, like Florida, for example, right? The cyclone is moving towards the land, but it doesn't hit on the land, but slightly tangentially move outward. Sometimes gets into the land, right? And then with a little uh, rainfall or whatever, strong wind, etc., it gradually comes out of the country back into the sea because of this Coriolis force. Okay, because Earth is rotating, it has this angular speed as well as a vertical speed. So when you combine these two together, you generate the Coriolis force. In robotics also, if you look at what we're dealing with here, the second link is on top of the first link. And the first link has a velocity, acceleration. This time it's velocity, angular velocity. And link 2 also has the same angular velocity. In addition to that, it has other things also. And also it has this linear velocity, right? It has a linear velocity because of its own angular motion, and it has an angular velocity from the previous link. Now, our discussion is the effect of this combination on the link 1, the preceding link, okay, link 1. So therefore, we take link 1 angular speed and link 2's linear speed, all right? So when you combine these two together, this is how the Coriolis force is calculated. The Coriolis force is proportional to the vector product of the two velocities, angular velocity and the linear velocity, right? It is q1 dot cross v2, q1 dot cross v2 and negative direction. Okay, so if you try to figure out what is q1 dot here, of course, as you can see, it is out of the board. Out of the board, that is q1. Okay, so like this, okay. Directly out of the board. What is q2? Q2 is seen here, is the velocity at the center of gravity, right? You can see v2 here. Now, when you do the cross product, what will happen? This is one of the vectors is out of the board, the other one is on the board, right? So q1 times q2, right? Cross product. So you generate the force this way, right? Minus q1 dot cross q2, as you can see it over here. So this force, when you break it down to again two components, you get FCOR capital T, this tangential force or normal force, and the other one is along the link, right? The cross product, and also the component is sine q2, right? Whatever the Coriolis force times sine q2, that is this one. And also you multiply with the distance, this time L1, you get the entire force that is on the first link, at the end of the first link, right? So that is why you have the term over here, the negative term over here. All right. Can you see it over there? You see q1 dot and q2 dot. Because q2 dot is coming from the linear velocity of the second link, right? That one over here, link is moving at q2 dot, and the distance is L2 by 2. So this distance times angular speed, that is a linear velocity. So L2 by 2 times q2 dot is v2, linear velocity, times q1 dot. And then you get the sine also, sine q2, and multiply with the length distance. So you generate that kind of torque. So this force is actually the Coriolis force acting on this link. So when you have this force acting on the link, the opposite force is reflected on the previous link, that is link 1. Okay. So it is trying to move clockwise direction, and to counter that one, joint 1 has to produce an anti-clockwise force, right? Same magnitude but opposite direction. So that is this tau 1 force. Tau 1 force. So remember it like that, okay? This Coriolis force, as you can see over here, is acting on the link itself, link 2. And when there's a force on that link, the opposite force is on link 1. And link 1 tends to deflect itself. To keep it from deflecting, joint 1 has to generate additional torque, which is calculated by multiplying the force times distance, okay? Right. So that is tau 1 force, that one over here. Then the last term is actually pretty easy to understand. That is the gravity term, right? Because without any motion, without any angular accelerations of joint 1 or joint 2, still the motors need to generate some torque to keep it in that configuration, right? So I'm at a certain configuration. If you just want to keep it like that, there's a torque joint 1 has to generate without any motion. So that is this one, M1G L12 cos Q1. Of course, this is trigonometry, to calculate the torque required at the joint 1, just to keep link 1 in that configuration. Okay. And the remaining part is link 2, M2G L1 cos Q1. Actually, you can work it out from here as well. L2 over 2 cos this Q1 plus 2 means Q1 plus Q2. Okay. That is tau 15. We have some graphics over there for tau 15. No, we don't, because there's no need, because pretty obvious. All right. So we broke down all of these 5 terms, right, of tau 1. This is the torque required at joint 1. For what? 1, to just keep it in that position, Q1, Q2 position, okay, against the gravity, number 1. Number 2, to maintain Q1 double dot, the angular acceleration of link 1. Number 2, to keep the same angular acceleration at link 2, so that they two will accelerate together, okay? And then to reject the disturbances, so fight with the disturbances coming from link 2 to link 1. So what are they? Because of link 2 motion, Q2 double dot, there's a reflected torque on link 1, and there's a reflected force on link 1 as well. So we have to counter these two, the torque and the force. So joint 1 has to generate more torque. Not only that, when the link 2 moves like that, it tends to fly away because of the centripetal force. And link 1 has to keep it in place. Okay. And also there is what is called the Coriolis force. And because of that, link 2 tries to get deflected. And link 1 has to counter that as well. So all of these terms are there for tau 1. So tau 1, joint 1 torque, is as complicated as this, as you can see over here, equation 1.62. Any questions up to now? Is everything clear? So let me ask Chaturanga, is that clear to you?
Yes.
Sandruan?
Yes, sir. Clear. And so we are expected to understand the physical phenomena with this stuff. That is the physical phenomena related to this each terms.
Yeah.
So in addition to that, do we need to memorize or something these equations?
I don't think you. So I think you are referring to. Not very sure trying to get at, but from my side, I want you to know the physical meaning of these terms, right? So if you are referring to the exam and what is coming in there related to this topic, I don't know yet. I have not thought about that, but most probably you will not be asked to derive Lagrange Euler, right? Formulation in the exams, right? So in dynamical systems, probably papers you might be asked to derive the equations, but in robotics, this is going to be open book exam. So what's the point of asking you to derive, right, any of these terms? So therefore, that is something I have to think about it, how to structure the paper. But for the moment, it's about physical understanding of these equations, because otherwise, when you look at this equation, it's a very lengthy equation, right? But if you figure out different individual terms, what is this term, what is this term, and so on, then you shed some light into this one and you figure out, oh yeah, so I understand this one. This is the centripetal force, this is the Coriolis, this is the torque that joint 1 has to generate because of the link 2, which is on top of that, has this acceleration and that kind of thing. The physical interpretation. Is that clear? Sandrovan, is that clear to you?
Yes, yeah.
All right. Taraka? Is this clear to you, what you are trying to understand?
Yep.
Right. Sulochana?
Yes, sir. Yeah, I missed very initial parts. I will catch it up watching
All right.
recording.
Yeah. So make sure so this document is specifically prepared for anybody to leisurely read and understand the entire thing. I haven't seen any single document on the same subject trying to explain individual terms with the graphics and all that. And that is why I had to write it myself, right? Otherwise, I try to use whatever available and use them with due credit to the authors, and I use it. Why do I write anything that is already out there? I don't do that. But this one, I couldn't find. So that is why I wrote it and I sketched some of these diagrams so that it's easy for you to understand. If you have time, maybe a couple of hours, right, to read the material, and you will understand it perfectly. Because mathematics is not that hard here, right? It is the time and the peace in mind that is required for you to understand the equations here. Okay, please do so. I'm not going to ask you to derive any of these equations in the paper. It's already given in the text. All right. So now you understand for joint 1 is bit harder because everything is on top of that. So there are a lot of disturbances coming through the link to joint 1, and it has to project the disturbances. Right? Otherwise, it will deflect. The link 1 will deflect because of all these motions, right, of the other links. So link 1 has to generate different torques, right, to cancel out all these disturbances because of Coriolis force, because of centripetal forces, etc., etc. And this one for a two-link manipulator clearly explain you what are the different components. Now you can imagine if it is a three-link manipulator, there are two links on top of the first link. So there are two centripetal forces, there are two Coriolis forces, and there are two acceleration related torques, force related torques, like that. It's even more complicated. Okay. But as long as you understand the process, don't have to be too upset about it. Okay. When you write down these equations earlier, I showed you, and if you continue the mathematics, the equations will fall in place. All right. Now we can carry it from there to talk 2. Okay. So this is a bit easier. Second joint over here, right? Second joint. So it's a bit easier for this joint because that is the last joint of the link. There's nothing after that point, right? So there's no joint sitting on top of this one, right, to produce any Coriolis or centripetal or any other disturbance forces, right? So therefore the torque equation for joint 2 is very simple like this. And where do I get it? I get it from the same equation from which I got this equation earlier for joint 1. So this is the dynamic uh, equation, Lagrange-Euler dynamics for two-link manipulator. And if you try to get the second equation of this one, you will see from the inertia terms, this term times Q1 double dot, this term times Q2 double dot, and these are zeros, these are zeros. As I said to you, see these zeros here, right? No centripetal force disturbance. There's no Coriolis force disturbance. Now see, now this is reassuring of our understanding about the physics here. We already know that there's no centripetal or Coriolis force disturbance on joint 2 because it's the last joint. There's no other joint sitting on top of that. So there are zeros. Okay, this one, and this one. And gravity terms is just one. Joint 2 has to support its own gravity. That's all. So it's just one component. You can see it over here. If you are joint 2, right? If you are joint 2, it is M2G L2 by 2 cos Q1 plus Q2, isn't it? Very easy. So this is the force due to gravity, right? And the torque generated by the force itself. That's why this L2 by 2 cosine term is there, right? The force times force is vertical downward, and it is acting at this length, right, of the joint. So therefore, you multiply the force times the distance, then that is the torque, like that. So let's go back to the equation and break it down. There you are, right? The gravity term is pretty simple. What about these other terms? The first term, this is because of the inertia. Of course, if you want to drive any link, right, with a certain angular acceleration, you have to produce this torque, inertia times angular acceleration, right? But if you look at this joint here, we call the inertia at the center of the link, right? But here, the joint is somewhere here, so you have to get the effective inertia as seen by the joint over here using parallel axis theorem. So that's why you get this M2 L2 square over 3 Q2 double dot, right? This is not the inertia at the center of the link, but inertia at the joint. And then you have the second term over here. That is something we need to break down. So T11 is all right. What is T12? Well, a moment ago, we understood that because of the acceleration of the second link, it causes a torque and a force on link 1. And link 1 has to compensate for that. So same thing happens the other way. Because of the acceleration of link 1, right, it produces a torque and force on link 2. And if the link 2 doesn't want to get disturbed, it has to generate or counter those coupled forces and torques from link 1. So this happens in both directions. The second term over here is the torque joint 2 has to generate in addition to, say, compensating against the gravity or generating required torque to accelerate itself, right? There are some disturbance torques coming from the previous link to this one. And that is why the term has Q1 double dot. Q1 double dot is the first link, right? This one. Because of the acceleration of the first link, right? There is some disturbing torques, right, on link 2. And it has to be cancelled out by producing opposing torque at joint 2. So how do you understand this term over here? we know that this is the other complementary term in the off diagonal, right? And we know that off diagonal terms are equal. And earlier we dissected this term for link 1. But for link 2, what is it? Right. Now look at these two diagrams and you will understand what is happening here. The first diagram on the left, if you look at very closely, you will see we start from link 1 and there is this acceleration, Q1 double dot. Okay. So this acceleration goes to all of the links on top of link 1. So the link 2 also gets the same acceleration, Q1 double dot. Okay, Q1 double dot. Now, so then if you look at the second link over here, right, it has some length L2 and there's some torque that it has to generate on the opposite direction in order not to deflect. So this causes some sort of deflection. So as you can see it over here, if I try to just move the first link, right? If you lock it here, that's all right. It goes like that, right? If you lock the second joint, it goes like that. But if you don't lock the second joint and you try to move the first link, it will go like that. It will go like that. Okay. The moment I try to move it up, the other link goes that way. It's like flipping something, right? It's like flipping something like over here, right? If I move it like that, it goes like that. That happens. So there is this clockwise motion happening on the second link, right? The moment you try to move it forward, it tries to move the other way around. You have to stop that, right? You have to, now when I say locking this joint, meaning that the joint has to produce the opposing torque, right? To avoid or keep the second link from tipping over like that, right? So this torque on the link 2 is its inertia, right? M2 L2 square over 3 times the acceleration. Okay, the acceleration is coming from link 1. You cannot change it because that is the requirement. You need to have Q1 double dot as link 1 acceleration, right? So therefore, the second link has its own inertia at the lower end of the link, acceleration times inertia is the torque, right? And the torque is in clockwise direction because it's tipping over the other way. And to keep it from tipping over, joint 2 has to produce the opposite torque. Opposite torque means the same direction as Q1 double dot. So the first diagram clearly explains that. So there are a lot of things, right? Eventually, though it's little two-link manipulator to take individual accelerations and how it affects the other links and all that is complicated, right? It's complicated. And then when you combine these two together, you have even Coriolis forces, sometimes difficult for people to understand unless you have the piece in mind, okay, to dissect the problem, unpack it, and figure out individual components inside. It's like a complicated device, say television or computer. You open it up, you can see the subsystems, blow your mind, something like that. So it's a big equation, and you can see individual terms and figure out what they are. That's the only way for you to understand what's happening here. But in the process, you will develop your analytical skills, and not only that, your discipline, your focus, and your being cool, handling complicated problems. one of the biggest problems for us, right, that holding us from being able to solve the problems is that you are not settled inside you, so that you are not ready to take different pieces separately and try to understand and solve. Trying to hold everything together, just can't do that, right? This is a basic example here. All these things are happening at the same time, but when we understand it, we understand separately. Look at the diagram on the right. What is that? So we are talking about the disturbing forces coming from link 1 to link 2. Okay, link 1 to link 2. Again, because of the angular acceleration of link 1, that is q1 double dot, right? There's an acceleration, linear acceleration at the end of link 1. And that is the force F here. You can see it over here. Force is distance times acceleration times the mass. Okay. So therefore you get L1 Q1 double dot times M2, because the mass of the link is M2. So mass times acceleration. So that is the force on link 1. Right? So this force is acting at the end or lower end of the link, and we separate resolve this force into two components, normal and along the link. Along the link force we do not discuss here, because it's not something the motor has to be concerned about, right? The normal force is different. The normal force here, as you can see, Ft is equal to the force, that is M2 L1 Q1 double dot times cos Q2 is the cosine of that force. And now you can see there's a force acting at the end of link 2, right? So the distance is like from the center of gravity, it's L2 by 2. So when you multiply with that distance, you get the torque. And again, you can see here, the torque is to topple it this way, clockwise. And to avoid that, you need to generate the opposite force, okay, anti-clockwise force. So when you add these two together, you generate the second term over here. This time it is Q1 double dot. Earlier it was Q2 double dot. Clear?
How that L1 term comes in for force expression?
Well, say it again.
In force expression, M2 L1 Q1. This L1 comes.
Which one are you referring to? These two? We have three terms.
No, sir,
Yeah.
in
So in
figure
this
2,
equation,
F
okay.
equals M2 L1 Q1 double dot. That L1
This
F
one.
equal, no, in low bottom,
This one.
no, middle one.
Middle one. Okay. This one.
Yes.
All right.
That,
All right. So you can see it there. It is L1 Q1 double dot is the acceleration. That part is okay, right?
L1 Q1 is, I mean, that L1.
L1 because the link 1 here has an acceleration, Q1 double dot, okay?
Yes.
Q1 double dot. So this acceleration causes, this angular acceleration actually causes a linear acceleration at the end of the link over here. At the end of the link.
Okay, so A equals R alpha. That's it.
Yeah.
Okay.
Acceleration is R, or distance times angular acceleration.
Okay, so okay.
All right. And then multiplied by the mass of link 2 is the force, and then resolve it normal and along the link, and then again multiplied by half length of the link to generate the torque. So if link 2 cannot produce these individual torques, then what will happen? The link 1 will produce the torque, and the link 2 will produce the mass. So this is the individual torques right? But what will happen is that when you try to move link 1, right, link 2 will topple the other way. You can experience this at home. Take a broom and try to be like that, right? As you all have done this when we were kids, right? Try to balance it. Now this time is a different experience. Try to pull it out like that. Give a little torque to link 1. This is link 1, this is link 2, right? So the moment you try to accelerate this one, this goes like that, right? It happens. So you move it like this, right? Then this guy goes that way, opposite direction. But what you want to do is this, okay? Remember, this is what you want. But if you don't have these two torques generated at joint 2, what will happen is that when you try to move it like that, right, it will fall over, right? The second link will fall over like that. This is, I think, really interesting thing. So more than the exams or anything, I want you to be able to understand these things. So what's the point of remembering equations, right? Absolutely no point. These equations are there to explain the physical phenomena. So therefore, you need to know the physical phenomena, right? Through the equations. Okay. Now, if not for Lagrange, we could have done this way. We draw the diagrams and forces and torques and all that, right? We can combine together and assemble this equation. We could have done it, right? Now we can carry on with the rest. Dynamic simulation for higher degree of freedom manipulators, right? What about the dynamic equation for 3-link, 4, 5, 6, like that? Then, in fact, you can write it this way. So you have the dq q double dot, that's the first part, all of the joints because of the acceleration, initial torques, right? You get this one. And you have centripetal forces, right? And the torques generated because of these forces. And you have Coriolis forces, right? Because of this connection between 1 and 2, what we saw earlier between the two torques, two links, there is this coupling, right? And now you have 1, 3 also, not only 1, 2, now 1, 3, right? You have to consider that also. And then you have 3 and 2. Now, when you have 3 links, right, this Coriolis thing comes in all these combinations, 1, 2, 2, 3, and 1, 3, right there. When you implement mathematics, you can it will naturally show up that there are 3 groups like that, and then gravity vector. Okay. So in a 3-link manipulator, right? We are discussing right now a 3-link manipulator. The DQ will look like this: D11 to D33, altogether 9 elements. Okay, 9 elements. And you have how many Christoffel symbols? Can anybody guess? Earlier with 2 links, we had 8 Christoffel symbols. How many this time with 3 links? How many Christoffel symbols this time with the 3 links? So it's number of links is the power 2 to the power number of links. Earlier it was 8. Now 3 to the power 3, 27. 27 Christoffel symbols. Just the number is big now, 27. Earlier it was 8 and we were able to manually do that. And this is 3 times or 4 times, right? impossible. You can do that. Once we do that, you can separate it out like this. See centripetal forces and the related torques in the dynamic model are actually represented by the CE matrix, right? This one, 1.66. And Coriolis forces, right? They come in 1, 3, 1, 2, 1, 3, and 2, 3, like this. You can see the Christopher symbols in all of these things, right? So Christopher symbols is very important, therefore. It represents the coupling between these forces in terms of what? Because of centripetal force and because of Coriolis forces, right? Right. All right. Okay. Now, see, here you are with the Christopher symbols C111 to C333, and you can see this is basically if you go back the centripetal matrix, right? Centripetal matrix, it has all these Christopher symbols and the Coriolis symbols of the Coriolis matrix between first and second links, right? These are the Christopher symbols, and the Coriolis matrix between the links 1 and 3. These are the Christopher symbols, and finally CCO Coriolis components between 2 and 3 links are these. Now you might be wondering, are they coming from heavens or randomly? No, there's a process, right? We have discussed that earlier, but if you want me to clarify it again, right? For every Christopher symbol, right, there's this equation. Now look at that one. This is for 2, 3, 1, right? And in this text, at some point, I want to go back and show it to you. It's there. CIJK is a Christopher symbol, CIJK, right? And you have the expression over here. So as you know, general Christopher symbol for IJK, you can write it down for any other specific Christopher symbol, C232, C233, whatever it is. You just replace I with that number, J with that number, K with that number. That's it. Okay, and this equation is there. You put it to that equation, then it becomes a combination of elements in the D matrix. So D is the inertia matrix, and you know the inertia matrix. You can get these terms there and differentiate with respect to a certain joint angle, and you get the Christopher symbols calculated. Okay, the process is there. What is intimidating probably is the scale here. Okay, now with the Christopher symbols, we have the Coriolis and centripetal forces all accounted for, and then the gravity term, of course, any manipulator, you can calculate the gravity, right? For each and every link, if you know the angles and all. So once you put all these things together, you have the dynamic model. But now what we are going to do is to do it in MATLAB for one of the most famous manipulators in the world, a legacy manipulator, Puma 560. Now you can see it over here, Puma manipulator. It's a 6 degree of freedom manipulator. Very interesting design because the first 3 links are actually non-zero links. They have certain lengths and all that. You can physically see it, right? This is the first link together, and this is the second link, this one, the third link, and fourth, fifth, and sixth, all 3 links are at this point here. You can see, let me make it a little bigger so that you can see it a bit more clearly. Anyway, right. So we are now going to take the first three links, and you can see J1 over here, this point. I'm showing you the corresponding points, J1, joint 1, and joint 2 is over here, somewhere here, joint 2, and this is joint 3 at this point. And joint 4, 5, 6, they are all here at the same point. I have not written it J1, 2, 3, probably I can update that. J4, 5, 6, they're all here. Okay. So we are going to take the first three links. The other thing I want to show you here is that if you look at these coordinate frames, right, you have earlier done the standard DH frame assignment. Okay, remember the 4 parameters, D, alpha, and theta. What's the other one? A, link length. So in the standard format, I think we followed that procedure. First is the joint offset D, right, and then theta, right, or Q angle, and then the link length A, and then link twist alpha. So that was the standard procedure. And that DH representation, the coordinate frame attached to a link comes at the end of the link. You saw that, right? If you have say link 1, start point, end point, right? The end point of the link, there you have the coordinate frame. Right? It's a bit awkward. We would rather like to have the start point, which is over here, and the frame is assigned at that point, right? Like origin is actually the base point or the lower end of the link. We would prefer to have it that way, but the DH table, standard one, says no, the frame is assigned at the end of the link, okay? But yeah, so standard kinematics, that's all right. But here, when you work with the dynamic models, you want to find out the center of gravity vector at this point with respect to the world coordinate frame. Okay, world coordinate frame. In that sense, it's a bit easier if had you define your coordinate frame at the origin, or rather lower end of the manipulator, not the upper end. So therefore, we're going to use a different coordinate frame convention here. We call it modified DH frame assignment, modified DH table. And this is what Craig used in his book, Industrial Robotics and Control, rather, right? The book by J.J. Craig. The frame is assigned at the beginning of the frame. And also that is the coordinate frame used by Professor Khatib at Stanford for many decades. So particularly for dynamics, the modified DH table is a bit more convenient, okay? Right. So that is why you can see it here. This is, again, not the standard DH frame convention. This is a modified DH convention, all right? Now you can see this is the origin of the link 1, and we have the frame 1 there. See that? J1, Z1, X1. So this is the frame at J1. The joint and the frame are at the same point. Whereas in the standard DH1, joint 1 is here, frame 1 is somewhere else. And look at J3. There you are. You have the frame right at J3. Right? Look at J2. You have the coordinate frame J2, second coordinate frame there. So clearly you can understand this is not the standard DH frame representation. Okay, this is modified DH parameters. So to help you with that, And first of all, why we selected Puma 560 manipulator? Because if you want to do dynamic analysis of any manipulator, you got to know the inertia, the link lengths, etc., right? You need to know everything about the manipulator. And if you just see some videos on the YouTube and all that, you see the manipulator, but where is the data? It's hard to find. Puma 560 is one of the most deeply analyzed manipulators in the world. So there are a lot of research papers where you can find out these parameters. So I have taken one reference by Professor Khatib and his students back then, a long time ago, and found these parameters for 6 links and the end effector, 6 joints rather, A, L, Q, and D, right? So alpha is the twist, and L is the link length, Q is the joint angle, D is the joint offset. So 2 parameters are in distances, millimeter here. Other 2 parameters are in angles. And Puma 560 is an all rotary manipulator, so that only Q column, right, is the variable column. All the variables are here, right? And other numbers are all fixed. As you can see, L2 is the link length over here. And these are the offsets. Okay, 671 millimeter, like that. And this is the end effector. If you want to put an end effector with a certain constant distance plus the tool, right? So at the end, you will see this one right over here, right? This point, anything that you attach, right? It will come like this as a joint offset, 51 millimeter plus whatever tool. Okay. Not only that, you need to have the masses, inertias, and all that, right? So for that, what Professor Khatib and his students had done a long time ago is that they have taken this manipulator and remove link by link, and then they measure the inertia and all that using various techniques. You can hang it using 2 threads and then swing a bit and calculate the period of oscillation. And you know the mass, you can measure the weight and etc., calculate your inertia. So there are various ways to do that. They have done this as a research and they have published these numbers. So we can use the same numbers for our teaching and research. By the way, and this is the coordinate definition of the modified DH parameters, alpha, L, Q, and D. Okay, this is how we define it. And before that, how do we assign the coordinate frames, right? It's already written here. Number 1, 2, 3, 4. There are 4 steps. Identify the axis of motion, Z1, Z2, like that. You draw the Z axis and draw X axis, assign frame 0, and like that, right? I don't want to confuse you because you have already done standard EH table, parameter assignment, etc., coordinate frames. Don't mix it up with this one, right? This is just for a record only. And I want to show you this one, the homogeneous transformation matrix, right? This one. When you use the modified DH table, this is the homogeneous transformation matrix between frame I minus 1 and I. In fact, this is the description of frame I with respect to I minus 1. If you look at I minus 1 frame, the previous frame as your reference, and U as I, the frame, right? This matrix shows you your orientation and position with respect to the previous frame, I minus 1. Now, in the standard DH parameter case, this matrix is different, okay? Right. Okay, so when you read the reference in robotics, particularly if you find out these DH tables and homogeneous transformation matrix, be sure to check what is the DH convention they use, whether it's a standard DH or modified DH. Okay, right. So these are the inertias of these links, IX, IY, IZ, at the center of the link. All right. You see principal inertia X, Y, Z. But in the dynamic model, it's not the principal inertia that we use. The inertia felt at the joints. Okay, so therefore this inertia has to be transferred using parallel axis theorem to the respective joints. So there's work to be done. And the mass of the links and center of gravity distances, you need all of these things if you want to implement the dynamic model numerically. Okay, and look at the first row here. This is joint 1, therefore it's about link 1, and the mass is not mentioned because you don't really need the mass here for the first link. If you look at over here, the diagram, the picture of the manipulator, it is the mass of this one, the cylindrical thing, right? It is only rotating around the z-axis. Okay, so it's not actually having any linear motion whatsoever for the first joint. So that is why we do not, you can measure it and keep it there, but in your equations, it doesn't come, right? Because it's only the inertia. So if you get a mass like this and only rotate it, right? You only need to take the inertia of that one, right? And of course, weight is there anyway, but if it is vertically acting along the link, again, the weight also is not something that the motor has to bear. The motor has to provide the rotational, whatever motion, right? Whatever torque is required for that. Therefore, mass doesn't get in the way. The first link only. The other links, you need mass because they're moving linearly, okay? Right. Right, so what's next? Then we'll go to the simulation of Puma 560 inverse dynamics. Inverse dynamics means you're going to calculate the torques required at joint 1, joint 2, and joint 3. What are the torques required? And for that, you need to have some sort of trajectory, right? That you need to go from here to here. For that trajectory, right, you can actually calculate what are the torques required, right? Okay, now let me show you the MATLAB here. Right, so here we go. In the simulation, we first use the DH parameters, right, as symbolic parameters because I'm going to use these parameters at different joints so that they get different values, not fixed values, right? So alpha, length, offset, and theta. Okay, 4 parameters, and I have joint angles, 3 of them, Q1, Q2, Q3. So they're all now variables. They are symbolic variables. Okay, right. So that I can use some symbolic mathematics here. Then number 2 over here, simulation parameters. So this is my strength of field of gravity 9.81 and my simulation time interval about 20 milliseconds for 6 seconds. My simulation is about 6 seconds. Okay, and this is my timeline, stamped timeline from say 0 to that particular duration in terms of 20 millisecond interval. So I'm going to generate about 300 samples. Okay, about 300 samples, manageable. Right. So this n is the number of samples in my simulation, right? Every 20 millisecond, I have a sample. Right. Then these are the link parameters from the from Professor Khatib's paper, A1, A2, A3, L1, L2, L3, D1, D2, D3. These are fixed parameters. So out of the 4 parameters in the DS table, 3 are constant, the other one is a variable. So variable is Q1, Q2, Q3. Now, center of gravity of the second one, third one are like this in X, Y, Z, right? With respect to its own coordinate frame. Uh, 2 and 3. COG1 is not required. It only rotates about its Z-axis, as I explained a while ago, right? This is the base point of frame 1. It's located at 0, 0, 0, right? XB, YB, ZB. So don't worry about it. Then the link masses M2 and M3. M1 is not required because it's only rotating length. Number 7, link and motor inertia from the standard paper, from the Stanford paper, right? This is the motor inertia, motor 1, motor 2, motor 3. I will come back to this motor thing. Right now, I'm only focusing on the link length and all, right? This is the IX2 XYZ, the inertia, right? At the center of the link 2 and link 3. And this is link 1. Okay, here we go. What else? Homogeneous transformation matrices. So it is T, alpha, length, offset, and theta. When you send these 4 parameters to this function, right, it will give you the homogeneous transformation matrix T. Okay, you have to calculate this whenever the position changes. Okay, because you can see it comes with the theta, right? Theta is this angle. So there are 3 homogeneous transformation matrices, T1, 1, 2, 2, 3, right? And then you have from 0 to 2 and 0 to 3 as well, because from the base coordinate frame, you want to calculate second link and third link, okay? So these transformations are there. Rotation matrices also you need to use in your dynamic model. These are the those vectors to the center of gravity of link 1 and link 2 and link 3. Then the potential energy of the 3 links, right? Obviously, it's just like this. When you have their vectors, right, you can multiply with the mass times G. Gravity terms, calculate like this. Then these are the linear speeds. So there you differentiate r theta, right, with respect to time to get the linear velocity. So differentiation in a symbolic format, right? We don't have to do it manually. So let MATLAB figure that out, right? RC1 and RC Q1, they're all symbolic variables, right? Because RC1 changes as the manipulator moves, right? We have set this RC1, for example, here. This is a constant, but this is not a constant. It's coming from the R02 here, which is a rotation matrix at different time intervals. It has different values. So they are all symbolic, therefore. Okay, right. Then 17, 16 angular velocity Jacobian is from the angular velocities that we write down after forward kinematics for orientation. Once you differentiate, you get the Jacobian. Okay. Then this is the kinetic energy matrix, or we call it D matrix. First three terms, right? Plus the rest. So look at this one. This is one long equation. What is that? M1 transpose JV1 times JV2. This is J transpose J. Remember that equation? Right, in our text, I can bring you to that equation, right? The pedal back quite a few pages. But anyway, it's interesting, this equation, but not like expanded like this. Is dq inertia matrix, right? So comes from here. That's that. Further down, further up actually. So this is for two link case. Here you are. So look at this equation. It is mass times JV1 transpose JV1 for the for that first link, right? And then J omega 1 transpose I1 J omega 1. So this is for the angular velocity, energy due to angular velocity. And this is for the joint 2, link 2 rather, right? And so on. So now in MATLAB, you write it mathematically or symbolically rather. M1 plus M2 plus M3 for the third link. Okay, so because of this symbolic mathematics, it's easier for us to implement this. Otherwise, it would have been very difficult, and also you can make mistakes in your calculations, right? Derivations rather. And immediately after that, once you have the matrix M, you can, I would have change this label as capital D, then you understand it is D, right? So D11, D12, D13, all of the elements in that matrix are already known, but in symbolic format, okay? Symbolic format. Then you can calculate the Christoffel symbols, everything that we have derived for three-link manipulator. Further down, over here. Now see, this is the centripetal term in the dynamic model. All of these Coriolis, Christoffel symbols are determined, right, in MATLAB symbolically by differentiating the D elements, D11, D22, and so on. They're all symbolic elements, and you can do the differentiation, right, as required by the Christoffel symbols. Now see all these things. Just label, you just write down these equations yourself, okay? Up to C333. Then centripetal torque is this one, CEN matrix, right? This one. And after that, you have three Coriolis terms, and you can see the Coriolis torque 1, 2. This one is 1, 3. This one is 2, 3. Okay, so you have done those three matrices also now, right? These three matrices. Now this is our dynamic model, the first one, second one, third one, fourth one, fifth one. Now you only need the gravity terms, right? Right. Then joint trajectory for simulation constant, joint acceleration. So I think gravity terms you have done somewhere else, right? So this is simulation loop starting over here. Q1, Q2, Q3, starting with the some joint angles, right? And then you generate your velocity, right? Starting with some acceleration here. Here you are. Can you see the acceleration given here? So what I do here is that I use constant acceleration, 0.2 radians per second square for joint 1 and negative 0.3 radians per second square for joint 2, negative torque, deceleration, and 0.4 radians per second square acceleration for joint 3, right? Understand? Then I start with Q0 and dQ0. So initially, all the joints are at 0 position, 0 speed, okay? And I use a constant acceleration for some time. And after k equals n by 2, right? N is the total number of timestamps in the simulation, 300 in this case. After 150 timestamps, I change the acceleration to their negative values. See here, 0.02, 3, and minus 0.04, right? The opposite of this one, okay? Right. So these are the conversion of the symbolic variables to double format, right? And get the numerical values, because in the loop simulation, you can't have symbolic math, right? You have to have numerical values to calculate, right? So you can have symbolic values, but you have to immediately calculate their numerical values. So that's what's happening over here. So then this is the dynamic equation, TOU, tau. It calculates all of the three torques, right? For the 300 samples in the simulation. And then I keep writing the data to data files. So yeah, and that is basically plotting. So let us run this code and see. So I'm going to run this code now. Yeah, so now the simulation is running. You can see the manipulator on the right bottom. You don't see much of a motion initially because it starts with 0 speed with some acceleration. But now you can see it's moving, right? The first joint is positive acceleration, second joint negative acceleration, third joint is another positive acceleration. On the left figure, you can see the torque, right? Look at torque 1, that is the first joint torque. Red one is the second joint torque. Third one is the third joint, tau 3. The amber color one is the torque at joint 3. So these joints are labeled with this black dot circles here, joint 1, joint 2, and joint 3. Okay. This is a 6-second motion, but it takes more than that, of course. You need to have a high-speed computing platforms if you want to implement this in real time. Okay. Now, after 3 seconds, it's halfway. We are still not there. At that point, acceleration changes to deceleration, signs change. And at that point, you can see the torque is changing a little bit, particularly for the first 2 joints. There's some sort of sudden change in torque because of the change in acceleration, right? And after that, it becomes a bit smoother. Now, because of the decelerations, right, the velocities some of the joints have got earlier are now reducing. So therefore, motion is slower now. And also because the negative acceleration initially, one joint got a high velocity in negative direction. Now it is also getting near to zero, right? So therefore, you will not see fast motion on the manipulator right now. Because of the smaller velocity, some of the strokes are also now smaller. Strokes are now getting to back to towards the zero level, right? It doesn't come to zero, but at some point. Yeah, I think the simulation is over. And now you can see the right lower figure. The red trajectory is actually the end effector, right? End effector at the end of the last link, the path it has taken from start to end. It's like a curvature, right? You can actually turn this and see for yourself, right? Actual path in 3D. And now after the simulation, we have some information visualized here, and the top left one is Q double dot acceleration of the first three links, right? Link 1, link 2, link 3, you can see angular acceleration in blue, red, and amber, right? So for the first half of the motion, you have some acceleration, decelerations, and the next half, all these things have reversed, okay? So look at the blue curve. It starts with 0.2 for half the time, and then immediately go to minus 0.2, right? All the other joints are the same. They have different values, but you can see the same pattern, plus and minus. Why I do that? Because it's the easiest to make you convenient in following this part of the lecture, right? And also you can see the second part, right? The middle top figure is the velocity, so joint velocity. You can see all of these joints, right? They continue in either positive or negative direction, and you can see continuously changing, ramping up velocity, right? Velocity is increasing at uniform rate, and at the halfway mark, they're coming back to zero, okay? And then bottom left one is the angle, right? You can see start with zero and settle down at some point at the end. And then torque and the actual visualization of the path it takes. So this is the real simulation, right? In the sense, all of the disturbing torques, everything is included here, right? Any questions about this visualization? Anything you want to ask about the simulation and these graphs? So let me check. Samira, do you understand what you see on screen and how you got those graphs and all?
Yes, sir.
Okay. Chaturanga?
It's okay.
All right. I know this is a bit tough, okay, but with all this help, illustrations, equations, everything, and maybe you need to review the lecture again, right? You should be able to understand and probably redo this, because the code is, and then the note the code is provided. I don't share the soft copy of the code for one reason, because I want you to code it yourself. You see the line by line thing, it's about 200 plus lines of code. You can type it yourself, and then you understand it. 200 plus is not a big deal, right? Anybody can write that amount of lines. So I'm not asking you to do this as an assignment or part of the exam. This is entirely for your own interest. If you can actually develop a dynamic simulator for Puma 560 with all this information available, that will be a huge learning curve for you, right? Something really, really serious, particularly for those of you who want to projects in the future in this area. Okay, right. So then let's say goodbye to MATLAB and come back to our note. So if not for this simulation platforms, this would have been very difficult, right? And frustrating. So now everything is pretty neat and nice, and you can very efficiently learn some tough concepts, right? Difficult, complex things. All right. So this is quite a journey today. And in the notes, I have posted the simulation at every, how many? Every 60 steps. Right, that's for 1.2 second timestamps. You can see it over here. This is beginning 1.2, 2.4, 3.6, 4.8, 6 seconds. All right. So you can see intermediate steps, how the manipulator moves. This is exactly what you saw in the simulation. And this is the illustration of the, if you look at the X direction, this is what you see from start to end. And if you look the same thing along Y direction, this is what you see. Okay. And if you look at from the top, you see XY plane. This is like this, and then this is what is called isometric view. You look at it from an angle, right? At an angle, so you'll see this one. And then these are the other graphs: acceleration, velocity, position, and torque. Right. Fine. So that is the dynamic model building and simulation. Okay. So the next thing is manipulator controls. So these are very closely connected together. So let's look at the basic controls for manipulators, right? So this diagram shows you one very straightforward way that you can control a manipulator, right? We start with the joint trajectory, right? 2.0.1 is centralized joint control. So meaning that, say you have n number of joints in your manipulator. For each and every joint, you have the profile already generated. It's joint profile, right? So when I say joint profile, I refer to what? Q dot, Q double dot, right? For all of the joints, joint 1, Q dot, Q double dot. Joint 2, Q dot, Q double dot. Joint 3, and so on. So that is what I have written here as this Q D K, and then Q dot KD, and then Q double dot KD. So K is the joint index. Joint 1, joint 2, joint 3. If you have joint 6, up to that point. And D stands for the desired. Okay, this is your desired trajectory. Remember, a few weeks back we did trajectory planning, path planning, then to trajectory planning, putting the timestamp and everything. You studied a lot of things, right? Triangular velocity, trapezoidal velocity, like that, or polynomials, right? Use whatever you want, doesn't matter, and eventually get me, right? The joint angles, joint 1, 2, 3, 4, so on. So once you have it, you present these profiles, right, to what is called the outer controller here. You can see it here, outer controller. Right? Now, outer controller knows what accelerations are required or desired or asked right, by the trajectory pan. This is the trajectory pan actually on the left. And it will check through the shaft encoders, right, the joint angles, the present joint angles. It reads from the shaft encoders the position of each and every joint in terms of angle, okay? And also it has what is called the tachometer to give us angular speed. Now I have the present position and speed of each and every joint. Okay, this data is available to the outer controller, this one. Now see, the desired acceleration and actual velocity and position, they are available to the outer controller. Okay. What the outer controller does with that information is that it generates Q double dot K. What is that? Q double dot K is different to Q double dot KD, which is over here. This is the desired joint acceleration for that particular joint. 1, 2, 3, 4, like that. And now Q double dot K is not the desired one, but command acceleration. So the outer controller is going to command the inner controller to get this particular acceleration out from the link, right? It may or may not be equal to desired acceleration, this one, okay? It could be slightly different. Now, what is the outer controller is doing when it is calculating this Q double dot K from the other three data that is available to it, right? So let's look at this equation. I just propose, shall we try this equation? So what is that? Q double dot K, right? This is the command acceleration for joint 1. Outer control is commanding, okay, get me this acceleration, get me this one, joint 2, joint 3, 4, like that. The command, okay? So I calculate the command according to this equation. So what is that? Of course, I start with Q double dot K D, the desired one, okay? Because I cannot forget that. So that is what is asked. So that is there. In addition to that, I take Q dot KD minus Q dot K, right? This is the velocity demand, right? Velocity demand. So there's a demand from the trajectory side to maintain the velocity at this level. But here you have Q dot K, actual velocity of that joint. Say joint 2 velocity, according to the trajectory, is, let's say, 0.5 radians per second. But from the tachometer for joint 2, it says that is 0.3. Okay, 0.2 is the required one, 0.3 is the actual one. So they are not equal. So you calculate the difference, this error, and multiply by again, okay, to giving some priority or make it stronger or weaker contributor in the equation. For every joint, you have a different gain. Okay, it's not the same gain for every joint. So that's why the gain is also joint dependent. So it is KD, K, right? You have studied proportional derivative integral controllers. You will immediately understand this is the velocity error. Therefore, the gain comes in front of that is the derivative gain, okay? But we also cannot forget the position. This is the desired position of the joint, right? At that point, it is changing. At that point, this is the desired position. And this is the actual position that's over there from the shaft encoder. Again, these values may or not be the same, right? There can be a slight difference between the two. So take that as the position error, right? Multiply with the gain. And now you know it is error in the position. So it's a proportional control gain, right? And we don't go to integral or anything, so we are fine with this one. So if you use this equation, we can calculate Q double dot K. Now, it seems logically correct. You want to correct your position error, you want to correct your acceleration error, velocity error, and also you want to maintain a certain acceleration, right, given. So everything is in place now. So let's proceed for what? To check whether this equation help us to track the profile as closely as possible. Eventually, the profile is the position, not the velocity or acceleration, right? When there's a demand, okay, to follow a certain profile for a joint K, let's say QKD. So that is the profile generated for joint 1. An actual joint position is Q dot K. So K is the joint, right? 1, 2, 3, 4, like that. So if we can get these two profiles on top of each other, coincident for entire duration, we have a perfect tracking performance. How can we assure that? Let's find it out. So you have the equation here again, right? Now what I do is I take this Q double dot K to the right hand side and make the left hand side 0, right? Then everything on the right hand side, I have written it on the left hand side here again, with 0 on the right hand side. So what is that? Q double dot KD minus Q double dot K plus KD times Q dot KD minus Q dot K plus KP times QKD minus QK. So you can clearly understand that the third term on the left-hand side is the position error. Second term is the velocity error. And the left term here is the acceleration error. Okay? Now, if you define your position error as, say, EK, to simplify the expression, EK is the joint error, desired angle, actual angle. And then middle term is actually the rate of that, E dot K. And the leftmost term is E double dot K. All right. So now if you take the Laplace of this one, you get to equation number 2.3. This is the Laplace transform of equation 2.2. You can see S square capital EK of S, that is the Laplace transform of the position error. Right, then you have the initial boundary conditions here, S times EK0, initial error, minus E dot K0, initial velocity error. If you don't know these values, you can set them to 0. That's fine in practical setup. But in theoretical setup, you need them, as you see over here in 2.3. So once you simplify this one, the second term you transform to Laplace, and third term is equal to 0. And you can now see EK is the common term, comes out of some of these terms, and you combine them together and move the other terms to the right hand side. Initial values EK0 and E dot K0, these things, and divide by the coefficient polynomial of S here. Now it's a control problem basically, right? Now the error, joint error, right? Control, whether it is stable or not, whether it is fast converging, slow converging, whether it is oscillatory, all these things can be analyzed using the denominator polynomial. That is S square plus KD, S plus KP. Very elegant and very easy to handle, right? So then let's take the denominator polynomial and set it to 0. Now, you know this, you have done this before, right? It's a quadratic equation, and you can find out the roots. So the roots of the characteristic equation are called the poles, and you have the two poles here, S1 and S2. And they are equal to minus KD over 2 plus or minus square root KD square minus 4KP over 2, right? Coming from this equation. Now, if you select KD and KP properly, the system can be made asymptotically stable. You know what I mean? For example, if we set KP to lambda and KD to 2 lambda, roughly, right? We could locate the poles as follows. S1, S2 is equal to minus lambda R. You can actually make these two poles coincide, right? On top of each other at minus lambda. Whatever lambda, you need to consider meet this requirement. Kp is lambda and Kd is 2 lambda. Just that. You use your Kd twice as big as your Kp. That's it. The moment you do that, you have a critically damped system. So you know what critical damped system is. Fastest convergence. So your error goes to 0 very, very quickly, like that. If you select your gains like that. What is the condition? If you have, say, 5 for the proportional gain, put 10 for the derivative gain. That's it. Then you make sure that your error goes to 0 like that. When the error goes to 0, you have the perfect tracking. The demand profile is actually being implemented by the controller. Right? All what is required is to calculate your torque demand using this equation. This is the torque demand. Okay. So that's why it is very important that you figure out some sort of control law, right? It's a simple equation. How you calculate the control input based on the reference signal and actual setup, position and velocity, right? And if you get this equation right, you can prove that your controller will drive the error to 0 for all of the joints and in the shortest possible time. So this is exactly what you want as a control engineer. All right. So that's the centralized joint control. If you have the entire trajectory in joint coordinates, okay. The next thing that we're going to discuss is Cartesian trajectory tracking. So what if your trajectory is in Cartesian space, our world, X, Y, Z, and orientation, okay? Right. So if that is the case, how do we modify what we learn up to now? Well, we'll modify the diagram slightly, and this time it is the Cartesian trajectory over here, not the joint trajectory, okay? It's the Cartesian trajectory. So that what we get to the control is xd, x dot d, and x double dot d. Now here x is the Cartesian trajectory. It includes the typical xyz position and also the three angles, roll, pitch, yaw, okay? And there are velocities, there are accelerations, all these things. And the rest remains the same. The outer controller reads the joint angles and joint velocities. Okay, they all come to the inner controller. Now, by the way, I want to pedal back a little bit to explain you something that I missed to explain. Now, how do you actually use this equation in a practical setup? What's the process? Now, eventually you decide over here some acceleration, okay? Some acceleration for joint 1, 2, 3, 4, 5, 6, like that, all of the joints. Now, what the inner controller has to do is to realize a torque, calculate a torque vector actually, 1, 2, 3, 4, 5, 6, all of the joints, right? which is corresponding to the acceleration vector here. Okay. And already it knows the joint position and joint velocities, existing ones. So that using existing joint velocities, you can calculate the Coriolis and centripetal forces. And using the joint positions right now, you can calculate the gravity terms, right? But in order for you to calculate actual torques required, you need the inertial terms in the dynamic model. And that can be calculated only if you know the angular acceleration. And for that, you have this one, Q double dot K, right? This is available to the inner control. So with the Q double dot K available to you and QK and Q dot K measured from the sensors, the inner controller can use the dynamic model of the plant, right? The Lagrange Euler, say for example, and put all these things into the matrices and calculate the torques, torque 1, torque 2, 3, 4, 5, 6, like that. And then these torques are to be realized in the manipulator, right? And you actually execute this, realize these angular accelerations, and therefore corresponding velocity, acceleration, position, and you drive the entire manipulator as close as possible to the joint configuration, right? Q dot, Q double dot for all of the joints. Okay, so every loop this happens, right? The inner controller calculates the torque required, right? Looking at the present situation, the position and velocities, everything, the configuration of the arm, right? So that will be a very efficient controller if you do it like that, because controller knows how much of a force and torque is required given these circumstances at any at all times within the entire control duration. At every single timestamp, the controller calculates the best or most appropriate torques, right, to each and every joint. Fine. Now, back to Cartesian trajectory tracking. The only difference is over here, right? How does the outer controller, right, generate Q double dot K? That's it. Earlier it was easy, but because it was entirely in joint control space, but now we are starting with the Cartesian trajectory. So how can we solve this problem? Right. So let's look at these equations here, right? X dot equals JA Q dot. So JA is the analytical Jacobian and Q dot is the joint velocity vector. So this is the typical differential kinematics. Remember, we have done this a few weeks ago. And if you differentiate both sides, X dot becomes X double dot. And that differentiation on the right-hand side is taken by parts. So first you differentiate Q dot to build a Q double dot, and then you differentiate JA to get JA dot, okay? That is the rate of change of Jacobian. And from there, you can actually get your Q double dot as the subject of the equation and bringing the other term to the left-hand side and by inverting the Jacobian. So this is 2.7 is the equivalent expression for Q double dot if you know X double dot. Of course, you need to know Q dot and Jacobian. And we know with the available sensors for joint encoders, we know the position, all the joints, joint angles, their values, and also from the tachometers, we know the velocities of each and every joint. So those are available to us. That calculating the Jacobian and getting the inverse of that is possible. When X double dot is known, we can put it there and calculate Q double dot as the desired joint acceleration. And similar to the previous case, where we wrote down this control equation to calculate Q double dot. This time we write it for Cartesian space. Look at the entire equation. This is Cartesian space equation, very similar to the joint space equation. Okay. You can see the position error. When I say position error, is the x direction, y z directions, right? Any errors. And also the roll pitch errors in the orientation. This is the velocity error, and then this is the acceleration demand. Okay. So with that, because this is known, acceleration demand is coming from the trajectory planning. It's there. The issue is how to calculate x double dot. So using this equation, you can do that. Now, rest remains the same. Kd is the velocity gain. Kp is the position error gain. Okay. Now, when you substitute 2.8, which is this one, in 2.7, look at that. From 2.8 to 2.7, x double dot. So you get the expression for x double dot and put it inside this equation 2.7 in place of x double dot, and you write it again like this. Equation 2.9. What do you have? You generate Q double dot. The demand, right? The joint acceleration demand can be calculated this way, right? Now, rest remains the same. Now, once you have Q double dot, look at the diagram here. Once you have the Q double dot for each and every joint, you can carry it forward through the control diagram in a controller, then generate torques and make sure all the joints actually follow as close as possible to their planned trajectories. Okay, so when it's happening, you will see in the Cartesian space also x demand, y demand, z demand, and roll pitch demands are matched very, very closely, right? Okay, any questions up to now? Taraka, the two control schemes, are they clear to you? Taraka, are you there? Resume recording, right? So now let's move on to our next discussion, or the last part of the of this chapter, motor and gearbox. All right. Now, if you remember, what we have discussed so far is actually the links, link one, link two, and so on, right? But at the joints, there's a motor and a gearbox. In our discussion, we have not discussed that specifically, and some of you might have already understood. Is it not a part of the link itself? So do we need to separately address it? Yeah, in a way you are right. They're part of the links. But this is the reality. The reality is that the motors and gearboxes are not that heavy, and they don't have a lot of inertia, rather, okay, compared with the link itself, right, which is going for maybe half a meter or so, right? Sometimes they have some inertia which is bigger than the motor and the gearbox, okay, if you look at the mass and all that. But when you are spinning the motor, you are spinning it very, very fast. Okay, motors are very fast. And then you use the gearbox to reduce the speed and get it to a very low value when it comes to the link. Links are moving relatively slowly, whereas the motors are spinning very, very fast. So the gearbox has different gear wheels running at different speeds. It is a bit complicated, right? But all in all, what we can say is that because of the spinning at very high speed, it has a huge inertia. It has a big inertia in the motor and gearbox, right? So the other thing is that now if you get a motor and a gearbox attached to it, and then comes the link, right? If you generate, this is not practically possible, but to understand the concept, if you generate a certain amount of torque, which is just enough to drive the motor and the gear box, right? Still the motion is not there, right? But there's already a torque generated. There's already a torque generated. Let's say you are driving a link at a certain angular speed, let's say 0.5 radians per second square, okay, that acceleration. If you take the link itself and link inertia and everything multiplied by the acceleration, you get a torque. And you cannot take that torque alone from the motor and gearbox, because to drive the motor, drive the gearbox, there is also a torque involved. So this torque and that torque added together, you get the total torque. So that is what motor has to generate. But that particular part of the torque that the motor has to generate to drive itself and drive the gear wheel at a certain RPM, that torque does not come to the link and cause any motion. Okay. So that torque is already spent within, it's an overhead. It's already spent within the motor and gearbox. It doesn't come out of that to the link. So therefore, it doesn't contribute to Coriolis forces, centripetal, right? It doesn't contribute to any of these other coupled torques in the system. But every joint need to generate this additional torque because of its own inertia and gearbox. Okay, it's very clear. So therefore, we better add this term in the diagonal. You can see the inertia matrix along the diagonal. You add this one. What is that? R1 square I1M. So this is the motor and gearbox inertia times the reduction ratio, R1 square. Because you know, particularly mechanical guys, they know about this. When you have a rotating body and which is rotated by a motor, okay, through a gearbox, and speed is reduced, okay, by a certain ratio, say 1 to n or n to 1. If it's a gear reduction, it is n to 1. N is a big number, integer, right? 100 to 1, 20 to 1, like that. So it is that gear ratio square times the inertia as you see it from the other side. Okay. So this R1 square I1M is the torque, the inertia actually seen by the motor, its own inertia plus gearbox, right? So this is the other one for the second joint, third, fourth, fifth, like that. So all of these additional inertias are to be added to the main diagonal. It doesn't go anywhere else. It doesn't go to off diagonal, and there's no coupling, because the coupled torques are actually, as you remember, the motion of link 1 generate a disturbing torque on link 2. So it's like that, or vice versa. But this particular torque does not come to the link. Motion is within, it is spent within the motor and gearbox. So therefore, you only need to add along the diagonal. In the MATLAB simulation we saw earlier, all these things are added along the diagram. Okay, so that's why that simulation is quite comprehensive, right? Now, can we use this concept as a smart design concept when it comes to designing the manipulators, right? And make the controls a bit easier. Yes, it is possible, and we call it dynamic decoupling. You already saw the inertia matrix is coupled, okay? You see off diagonal elements from link 1 to link 2 and vice versa. So link 1 to link 3, 3 to 2, like that. They're coupled. So this coupled dynamics makes things a bit complicated, all right? If you can decouple, right, joint 1, joint 2, joint 3 separately, then is relatively easy to deal with it. You can only get the joint 1, joint 2. You can forget about other things. Coupling can be neglected. So how can you do that? For that, let's use this inertia matrix here and put some numbers in. What about these numbers? Mass of the link 1 kilogram, mass of the link 2 0.6 kilograms, and what else? Link lengths. First link is 1 meter, second link is 0.8 meters. What about inertia of the first joint motor? It's very small. Can you see that? 0.005. And for the second motor, even smaller, 0.004. Okay. And when you substitute these numbers to the inertia matrix over here, right, you can actually get some of these things calculated numerically, not everything. It depends on cos theta, etc., theta 2, right, or Q2 rather here. But most of these numbers are actually numerically evaluated. So when you do that, this is your matrix. This is your matrix. Okay. And there you can see this R coming in. R is the gear ratio, R1 and R2. Now you have a choice to choose your gear ratio for the joint 1, for the joint 2, right? For your advantage, actually, right? You give a value and see for itself, right? So if I put, say, R1 and R2 equal 100, I choose a gearbox of 100 to 1. Then you calculate your mass matrix or D matrix like this. So what do you see? Right? You get this one, 51.061 plus 0.48 cos Q2, and 40.128 along the main diagonal, and off diagonal you see 0.128 plus 0.6 cos Q2, and there are 0.128 plus 0.6 cos Q2. You can see that the off diagonal elements are getting increasingly smaller compared with the main diagonal elements, right? And you can approximate this to this one if you want, right? Off diagonal elements are actually 0 compared to the main diagonal. The off diagonal elements are actually coupling, right? So you have reduced coupling very seriously. Now it is basically diagonal elements that are there, right? So this is what is called the joint decoupling using gear ratios. And if you look at the data sheets of some of the manipulators, you will see gear ratios like 60, 80, 100, 120, 150 even, right? Because of this reason. Then you don't have to deal with a lot of mathematical equations in your controller, right? To actually calculate the coupling forces and torques. So anyway, whenever there's a lot of coupling, it's not good because you have to generate a lot of torques and time varying nonlinear, right? Just to compensate for these disturbing torques coming from other links. All right. That's end of the lecture today and also the end of the section. Any questions? All right. So we are out of time as well. Let's wind up the session today, and I'll see you next week.